Hello. Okay. Yeah, so welcome to this Monday session. I hope you had a kind of an interesting session last week with the software. Yep. So let's try to make a recap before we continue. Today we are going to cover some missing things. I had to cover more in detail from last lectures. And then we are going to go very quickly through NPV estimation, calculation, and then the last part, if we have time, will be on starting on boosting, okay, subsea boosting. Okay, but so far we have focused, I think we have this tentative plan, okay, to estimate the performance of the field. Basically, we want to calculate production profiles, how much the field will produce in time. And for that, we're looking at different approaches. Okay. Yes, so we covered what is IPR, TPR, choke, network. I showed you a bit. Downhole network is the same as surface network, but inside the well. And now the part which is missing is boosting and artificial lift. Okay, we are going to have some discussion on that. I'm going to give some comments today about coupling that I think you already got from the exercises here in class. You already got an impression what what the word coupling means. See. Okay, and yes, and the NPV we will try to give some comments today. Okay, but I think we should start with simply coupling. What is called coupling? They call it production. Okay, sometimes it's called network. Sometimes it's called even well. Okay, simulator. And that simply means you have one model, which is a reservoir model. Typically, it's used to estimate how much the evolution of recovery factor in the field, evolution of pressure in the field, and it only contains maybe down to the wellbore interface, okay, to the sand face, or can also have, if you have tubing tables, can also include the flow in the wellbore, okay, but you need to have tubing tables. So this guy here is restricted to this is all in porous media. Okay, let's see, just the porous media. Here we can have the wellbore can be included, wellbore flow can be included. With tubing tables, okay, which we did a short discussion the week before, and basically is computing saturations, pressures, rates that I produce from the wellbore, but usually doesn't include any more than that. Okay, and it's something that is by itself, by nature, is transient. Okay. Well, you have this next part, which is it takes care of all the flow that you have to take from the bottom of the well all the way to the separator. Okay, so here you have the flow line plus pipeline plus wellbore flow. Okay, is typically steady state okay, which is that this derivative that you have with respect to time is equal to 0. Okay, and the assumption or the justification that we can use as steady state is that this evolution on the reservoir is so slow that we can simply take simple slices in each time and we can check how much pressure do we need. Okay, it's like we look at all of these different slices because it's so slow that the transients really don't matter. I can look at each one of these slices in time as a steady state. Okay, and here typically this runs with IPR, that you know, inflow performance relationship, has boundary conditions, on the well. Okay. And as I told you, we typically, now it's becoming more and more common to use coupling. Companies see that really it's not enough just to take this part alone with tubing tables or without tubing tables or with a minimum flowing bottom hole pressure, but actually I need to have this part, okay, to see how much that impacts my production profiles. Okay, it's becoming more and more, not trendy, but it's becoming more and more accepted that I have to have this coupling between the two. Okay. And some of the challenges we have discussed before, they belong to different departments in the company, different people in the company, different expertise in the company, so it sometimes can be challenging to communicate and to integrate these two models. Okay, they are also made in different software. But just, you know, I think we have done this diagram in the past. You save it. Okay, so we have on one side we have reservoir simulator, and on the other side we have this production simulator. And remember, be careful with the word production, because production, you know, I call the production system to everything from reservoir to wellbore, but production is typically, as a discipline, is typically seen as occupied about wellbore flow, flow line flow, pipeline flow, separation, okay, processing facilities. That's what we refer by production. Yeah? And we have some split in between. Okay, and at every time step, okay, let's say a time step equal 1. Okay, I estimate PR, okay, that can be for pressure in every cell. Okay, I can estimate saturation in every cell. Okay, you can estimate. What else can I estimate? Sorry, I cannot. Pi? Okay, permeability, yes, relative permeability, right? Yeah, sorry, you're a bit far away, so. And my hearing is not the best. Okay. But so you need to, at each time step, okay, a way that we say, and this is explicit, okay, this example that we're going to put here, example of explicit strategy, explicit coupling strategy. Okay, so I have those numbers and I have to transfer to the production simulator, which is steady state. For that particular time, I transfer some information that either I have in my production simulator, I have an analytical model for IPR. Okay, I have made some analysis and I have found, for example, I can use this back pressure model that we have used before, right? QCR PW PR squared. And in this case, I just need to, for example, if I was using that equation, I simply need to update reservoir pressure, right? Because the C and the N really don't change. But if I have, for example, a undersaturated oil, then it will be something like that. Okay, where I have to update the J doesn't have to be updated, usually remains constant. But if I go and become more and more complicated, okay, then I might use, for example, a Vogel. Okay, let's put that here. In which is not so trivial. I have to find a way. Each model has a way to say how do you update. In this case, I don't have to update just PR, but all this Q max. Okay, and I have to find a way to update that Q max with the properties. Sometimes I need. You go to one exercise. Was exercise 3. Okay, where you are using this equation, the back pressure equation, and then you are updating the C with the relative permeability of oil and the viscosity, the change in viscosity of oil and BO, okay, and reservoir pressure. So each model that you choose will has a way to update it with depletion, okay, or you can simply generate IPRs from the reservoir simulator. So we call it generated. Simply I go and I do some method to calculate the IPR of the well. Okay, and that method can be you run a multi-rate test. There are different methods. How can I generate this IPR? After that, I go and I use that as an input to my model. Okay, either the analytical IPR or the generated IPR. And what do I need to run the network? Okay, that's something we have learned the week before. To solve the network, if it's operating at let's say fully open choke, okay, simply I don't need anything else. That's the only thing I need, the new IPR, and then from there I can compute rates, right? From there I could compute Q oil, or let's call it simply Q well I, okay, and also maybe PWFI, and I can calculate many other things. But if I'm not in the fully open choke mode, what do I have to make? If I'm, for example, in the plateau mode, I need to have here also some, let's say, choke opening, right? I need to have for example, if I have pumps, I need to have the ESP frequency. Okay, what else can I control? Something that I can control, right? If my network, my production system has chokes only, that's the only thing I can change, okay? But if I have, for example, electric submersible pumps, that's what ESP stands for, then I can regulate the frequency on each pump, okay? If, for example, I have gas lift, right? I have gas lift injection on the wells, gas lift rates, okay? And besides that, I also need to have target rates, right? I typically have, because these reservoir guys, they have said you need to have, if possible, I need to get some rates, right? Some target rates that they have indicated that's the best for depletion of the reservoir. and can be something given by will, can be given by field. Okay, like in our case, the Snövit, we have said we want to produce 20. Okay, that came from maybe negotiation with the customer, maybe came from optimal reservoir development, maybe because of sand production limitations. Okay, and remember here, if we have that case that we have a target, okay, then we sometimes need optimization. Okay, what we call optimization inside this model. That we have done it with Excel, right? We have said we want to achieve these rates, and then we use Excel to change the delta P of the choke to get exactly that rate. Or you have also seen it in GAP, okay, when you were doing the exercise in GAP last week, that you said you had, when you set up the constraint of 20 million, then you see that you have two loops actually. You have the solver and you have the optimizer on top. Okay, you remember or not so much? I hope you remember. Okay. Then in an explicit scheme, simply you send those numbers back to the reservoir simulator. Okay, and now the reservoir simulator imposes those rates on the sand phase. It says to each well, now this is the rates that the network says I can produce. Okay, and can either be equal to the target rate or it can be different. Okay, I bring them back to the reservoir model and I compute the time step T2, okay, PR, SO, SW, SG, and then everything is repeated once more, okay, for the next time step. Okay, and let's say here and repeat. Okay, I hope that's clear. That's what they mean by coupling. Okay, you have two simulators. They can be from different software, different company, but that's actually what it means. I go check the rates. I can maybe produce the target rate. If not, I calculate new rates, and then from there I compute. Assuming these rates can be produced, I compute the next time. Okay. Okay, and there are other, so I think in the compendium we have a section if you want to read more in detail, and I think I gave some references for those of you who are interested in coupling. It's just at the beginning. Okay, I call it material balance because that's really what you use: the saturations, pressures, then you compute the well IPR, run the model, you find the results, you transfer, then you see how much I produced, and then you solve again the equation. Okay. If it's a reservoir simulator, it's slightly different. Okay, in this case, the reservoir simulator is computing the IPRs. Yeah, let me copy this. So on page page 19. Okay. What does it mean to make it implicit? So that is explicit because I don't redo, let's say in T2, okay, I'm assuming the rate remains constant for this step, okay, from T1 to T2. It's like this rectangular approximation, right, for the Q, for the cumulative rate. But it might be that at this time that rate is not feasible, okay, that rate that I have imposed. And then I have to find, actually I have to find a rate for time 1 and a rate for time 2, and the QP, how much I produce, is simply, I can make a trapezoidal integration, right? But for that I have to redo the step. For that I have to redo T1 and T2. So I leave it to you to think about it. Okay, there are many papers describing that, but just, you know, keep that in mind. I can also have implicit coupling. Okay, and there are different methods to do implicit coupling. Requires either, so some approaches people have done to make implicit coupling, solving all equations simultaneously. I think maybe I have an example. Okay, so you have to make a system of equations that you include also, in this case, these authors, they have a reservoir simulator, and they included in this reservoir simulator the network equations. Okay, so if you see here at the end, they're giving an example of the matrix system, okay, where part of it are the reservoir equations, okay, and part of it are the network equations. Okay, so you try to solve everything at the same time, which might not be suitable if, for example, you have the two models are from different companies. Okay, they usually don't give you access to the equations, they don't give you access to the source code, so you cannot make that integration. Okay, so in that case you have to do it manually, and then it takes more time. Okay, so basically solving all equations simultaneously. Also, you can rerun the step until some convergence is achieved. Okay, for example, you estimate rate, then you calculate the next step, you see how different the rates are, they are very different, then you redo the step until the rate is exactly the same. Okay, so you have some tolerance how many times you need to redo the step. That more or less clear? Yeah, I don't want you to be experts in coupling, just I want you to know the minimum, what does it mean, and why do we need it. Okay, and you're basically doing coupling in all the exercise we have made here in class, and also in GAP. Okay, some sort of coupling. You are taking reservoir model, calculate production, and then bring back rates. Okay, that's everything that we have been doing so far in class. But when we go to reservoir models, it becomes slightly different, a bit more complex. Now, on another topic that I thought was we have to complete a bit was how to choose tubing size. Okay, how do we choose tubing size? It's a big decision when we are designing a field to see what diameter of tubing do we have to put on the well. Okay, so what factors do we have here? How do we decide which tubing size do we use? Well, one is the obvious, right? We simply want to maximize production. And if we make the case for dry gas, okay, Remember, let's make bottom hole equilibrium. Okay, we have a well. Let's say we have a constant wellhead pressure, or is very close to a separator. Okay, and we're making PWF. And I told you one curve will look like that, one curve will look like that, and that this guy is IPR and this guy is TPR. So the tubing diameter, is it affecting which curve? Okay, the TPR, right? So if I increase the diameter, what should happen with TPR? Okay, everybody agrees? Yeah, I have less frictional losses, right? The origin will still be the same, right? Because there is simply hydrostatic pressure, and it doesn't matter if I have, if capillary pressure is not an issue, right? It doesn't matter if I have a 1.5 inch or if I have a 9 inch. Okay? I should have the same hydrostatic pressure. So that will be if I increase the size, or if I decrease the size goes on the other side. Okay? So this direction is actually, let's use another color, it's increasing with diameter. Okay, so you might see simply we want to increase the diameter until this rate becomes large. Okay, but there is the IPR has typically, so it's not exactly, but it has a region where it becomes actually quite vertical. Okay, then no matter how much I increase the rate, okay, actually the gains that I get, how much I increase the diameter, the gains that I get in rate, they're not really that significant. They're not really that much. Okay, so then you have to compute always what is the benefit or the gain, economical gain of increasing the tubing size, because it's also costly. Okay, it's also increasing the cost of the well. Okay, compare with the gain that I'm going to get in production. Okay. So let's put that comment here. Compare production gain tubing cost. Okay, and it will flatten out. So if you increase the diameter, initially will give you a very high rate, nice rate, and then it suddenly will start to flat out, and then it becomes very expensive to buy a big tubing simply to get this additional extra rate. Okay, so one thing is maximize production. Also you want to reduce cost, reduce well cost. What other constraints do we have? Yes? Hmm? Yes? Some liquids. Okay, he came to a key part here. But before going to the liquids, so simply has to fit the production casing, right? What is the typical production casing size we use in the North Sea? Is it 9 5/8, right? 7 inch. Well, we put it here and we have to ask a driller. Okay, now I thought it was 9 5/8, the production casing. Okay, one thing also is that you have the tubing hanger. Okay, on the size, say on the tubing hanger. Okay. And in a very simplified way, remember the tubing is hanging, we have here our production casing, a bit exaggerated. Here you're saying maybe 7 inches the production liner. The liner, right? The production casing I think is 9 and 5/8.
Yeah, the liner is also greater than 7 because production open hole size is 8.5, so that
Mm-hmm. Okay, so but the production casing that you hang here on the wellhead, I think that's 9 and 5/8. Okay, but I will check with our driller colleagues. Okay, so you hang it with, you have to screw it on this guy called a tubing hanger. Okay, that makes a wedge against the next ball of the production casing, and that's what we call the tubing hanger. And here the main thing is that I have, if you see it from the top, I have maybe the hole for the tubing, okay, which is usually screwed, or maybe it can have also like a wedge type arrangement, but I have also all kind of ports, all kind of penetrators to interface inside the well. Okay, I might have some, if I have a pump, I might have the ESP power cable, I might have instrumentation line, I might have if I have a gauge, okay, a downhole gauge, I might have also the just to simply to be able to communicate with all kind of equipment that I have here. The SSB, I think we had a comment last, I think it was 2 weeks before. Okay, we need to have a hydraulic line, and that hydraulic line has to go through the hanger. Okay. So especially for these wells in the Norwegian continental shelf, I usually had a lot of things going through that hanger. Okay. So if I try to make simply the tubing size bigger and bigger, it might be due to all the things, additional things I have to have in the hanger, that I cannot go higher than some size, okay? Because it simply will affect the mechanical integrity of the hanger. Okay? I cannot put too many holes in this cheese, otherwise it's going to collapse. Okay? It won't be able to hold the whole weight of the tubing. Okay, more or less because of that. What happened here? What are other things that we have to take into account?
Is it possible to change tubing hanger if we decided like we want larger tubing size, so we can change tubing hanger because it's on the wellhead, so
you can change it, but it's also depending how many things you want to send down. Okay, if you're still going to change it, but you will have, you know, still 5 ports going through there, you still are limited, because the hanger, actually you have this hole which is limiting. Okay, you have the size of the production casing. Okay, so you maybe can put a more robust tubing hanger, but actually if you have 5 ports here, that's what's really limiting the size of your tubing. Okay, how big can you go on your tubing? Next step is what you were saying about the liquid. Okay, okay, for example, especially very relevant for gas, typically gas is never alone. Okay, it has always some liquid associated, that it comes either in droplets or is attached to the wall and the gas is flowing up. Okay. So to lift this liquid to the surface, actually I need a minimum gas velocity. Okay, that I need to, usually the velocity of the gas, and we call it superficial velocity, which is defined as the rate of gas divided by the cross-section area, and that's the local rate of gas. Okay, that FSG has to be greater than some liquid loading velocity, critical velocity. Okay, it's called critical. Okay. Otherwise, I won't be able to lift those liquids, and the liquid will start to accumulate on the wellbore, and they will create a large back pressure against my formation. Okay, And one way to do that is simply to make a smaller tubing diameter. Then I reduce this guy here, and then I increase the superficial velocity of gas. Okay, so I have to be careful of that. And one more thing I have to be careful also is the erosional velocity. Okay. Also this V, SG, okay, has to be less than the erosional velocity, okay, which is given by API. Any of you remembers? The erosional, I think it's 14, is it 14E? Okay, erosional velocity, page 23. Okay, and it tells you a way how do you compute the erosional velocity. In this case, this API has a very simple expression, okay, that depends on the density of the mixture, and you have simply your velocity has to be less than that. Okay. Maybe just take that. Let's take that equation. There is another Norwegian standard, NORSOK, that has a slightly different expression, and I think that's what they use in Norway. This is used more in the rest of the world. API 14E. Okay. Okay, I forgot the name of the Norwegian. I think it's the NV 15 maybe. Okay, here 0501, recommended practice 0501. Okay, that's what we use here in Norway. We don't use the API too much. They use this 0501. That is API 14A, and this is DNV. If you're going to be working in the Norwegian continental shelf, this will be in Norway. That's the one we use. Okay. So you see, it's a very, so simply we want to get more production, we want to reduce cost, but also there are some mechanical constraints. How big can I go on size? And there are also some other operational constraints, okay, that I have to care. If I have liquid, that also happens in oil wells. If I go too big, then I start to have slugging, okay, which is like unstable flow regime. And also if I put it too small, then I might have erosion, okay, and that affects the life of the tubing, will be much shorter. Okay, what about we take a break? Okay, 15 minutes. Yes?
I have a small question. In Norway, what is the standard of operation? Does the tubing size determine the casing, or the casing determines the tubing size?
It's standard, so the conductor surface intermediate production casing usually is standard, is a given size.
Normally, from all of this calculation, you determine your optimum tubing size. Then, when it comes to well construction, the tubing size from the production team is, I mean, the well construction team then makes the casing design based on the tubing size.
Yep. For example, let's say you are doing your production analysis, right? You find that you need a 10-inch tubing size. It's not going to happen, okay? They tell you, no, we cannot that's not the way we because we have a certain specific size, standard size of conductor, intermediate, surface, and production. Okay, what might change is, for example, in the completion side, if you have a liner, you can change maybe slightly the open hole size. You can change maybe slightly the liner size to get a bigger well. Okay, but in terms of what you drill in the surface, usually it's the same standard hole, usually with not many changes. Okay, I think they have been trying for a time to try if it's smaller. Okay, if you say that you want 4-inch, for example, what if you drill a slim hole? Okay, then to try to make it cheaper, to try to say, well, I don't need a conductor so big and I don't need the production casing so big, but they can be much smaller. Okay, but usually you're a bit restricted, and then if you need bigger or smaller 7-inch, then you start playing with the completion part. Okay, with the liner, with things that are not hanging on the wellhead, things that are hanged much below. Okay, I hope that answered more or less your question. Take a break, 15 minutes. So now the next thing I want to say, also a bit brief, it's to make decisions. During field development, the company usually uses employs some economic indicator. Okay. But I told you, you have to go from decision gate to decision gate, and from there you have to neglect, or you have to go away from decisions which are less attractive, okay, than others. And one of the factors, taking into account, you know, the technical considerations, some constraints that I have, one of the main factors is some kind of economic indicator. Okay? And one of the main economic indicators is called NPV. Okay? And I guess all of you have heard about NPV. Yeah, there is a course actually called Petroleum Economics. All of you are taking it?
It actually coincides with this course, so many couldn't take it.
Okay. Yeah, that's a bit bad. So, okay, net present value. And there are other things that we are not going to talk about. And actually, what I'm going to do here is a very simple discussion about, basically about NPV. Okay. And the methodology we are going to use to compute NPV will be sort of simplified. We're going to make it such that we don't add, for example, taxes, depreciation, amortization, any of these things, okay? But if you want more details, you can go to the course of Trikve, hopefully maybe next year, right? If you are eager to learn about petroleum economics. What is the code of that course? Any of you remembers? But the code, do you know? 25 5116 0. Okay, TPG, petroleum economics, and the professor lecturer is Trikve Ström. Okay, so there you can learn actually better than what I can teach you here, but for our things, for our calculations, I think it's good to see a bit the economical part, okay? Because many decisions are basically made on economy, some kind of economic KPI, okay? We call it this is KPI, key performance indicator, and we are taking decisions based on that, okay? So we just want to see how it is calculated, but be aware, what I'm going to tell you here is not the whole story, okay? We have complicated methods to include, especially equipment which is going to be depreciated, so you can simply add that as a depreciation. Also, you have to pay for during the first years of production, you usually have some tax deductions that you can claim. So you have all kind of things that we are not going to be covering here. Here it will be very basic economics. Okay, but first, something that you have to be aware of is each company creates what is called a value chain model. Okay, and the value chain model is basically, I use it to compute this economic indicator, but I have like all the main elements of the field. Okay, so for example, I have the reservoir. Let's see if it fits. Like every year is a bit difficult to, like a small experiment. The reservoir is central and is what takes, you know, the most effort and the most time, and I have the most specialists working on the reservoir. Okay, and here I use it in a very simplistic way initially during early field phase. I use it to estimate reserves. Okay, reserve estimation. Okay, I need a few things to make my reservoir model. Okay, like reservoir structure and volume. I also need the rock properties, petrophysics, and also very important, I need the PVT. Okay, the PVT, some sort of PVT model. Okay. Then I can use that model. Sometimes I simply use that directly. If I already have a reservoir model and I don't do any coupling, I simply can use that to compute production profiles. And these production profiles is what I use later to compute revenue. I calculate the revenue stream. Okay. Here sometimes I have the production schedule. Okay. Sometimes it's simply embedded with the reservoir model, sometimes it's separate. Okay, and I might be because I'm compensating the production of this field with the production of another field. Okay, or that it depends how much, depends about the drilling. Okay, how many wells do I have drilled by that time? Yeah. To calculate the revenue, what do I need here? I need the hydrocarbon price. Okay, to calculate the revenue stream. Revenue stream, what should I include here? Here is sales. Remember, we shouldn't neglect never, if it's even a gas field, sales of condensate, gas, oil. Okay. The only thing we cannot sell is water, right? Not yet. Maybe we'll find a way to sell water. LNG, LPG, NGL. Okay. Then after that, that revenue goes to some economic evaluation. Let's see if I get enough space. Okay, that instead of calling it NPV, in our case, we're going to call it simply economic evaluation. And that usually needs, if I'm operating in a particular country, needs also the tax regime conditions and the royalties. Okay. And to compute, then I compute simply the income, right? And I have also to compute the expenses, how much that's going to cost. And to do that, that's something usually I don't have too much idea initially. Okay, the reservoir might have a roughly idea how much I will be able to produce, the volumes, the liquid, but then I have to know how much developing that will cost. Okay, and there is a large uncertainty if to use 10 wells, 20 wells, 15 wells, injection, no injection, what kind of injection, what offshore structure. There are many things. So in this part of the value chain model is where I have the greatest uncertainties usually. Okay, and let's say what I call the production system. Okay, depending on the size of the reservoir, the type of fluids that I have, the rates that I will produce, I have to define my production system. And here I have wells, which is almost like a separate department, gathering system, or what we say network. Okay, if I have any network, maybe I have simply wells producing to a platform. The well is drilled from the platform, and then I have no network, no subsea network. Then I have topside, which are my processing facilities, and then I have, which is one of the biggest items that are account for expenses and cost, which is the offshore structure. And this I have divided into my what kind of called production system, and this defines so here I think becomes a bit messy because everything affects everything. The production profile, how much I want to produce, affects all of them. Okay? And we have 4 main cost items that I want to put here. CAPEX. CAPEX stands for capital expenditures. Then I have DRILLEX, which stands for drilling expenditures. Then I have OPEX, which stands for operational expenditures. And then I have ABEX, which stands for abandonment expenditures. Okay, so here is a bit difficult to exactly decouple what is affecting what, right? But actually the wells are affecting the DRILLEX. Okay, also might be affecting a bit the CAPEX. Gathering system, topside, offshore structure, all of these 3 are affecting CAPEX and are affecting also OPEX and are affecting also ABEX. Okay. Also the wells, the type of wells that I have, they also affect the maintenance, okay, so affect the OPEX. So it's everything kind of interlinked, but I'm trying to make a diagram just to show the first order kind of connections between all of these items. Okay, and finally all of these costs, they enter into this economic evaluation. Okay, and at the end this economic evaluation spits either this NPV value, okay, the internal rate of return, and or sometimes we have the break-even hydrocarbon price. Say to make this project profitable, I need to have the price of oil can go as low as $20 per barrel, for example, 15, 40, 50, and that gives you an idea of the robustness of the project. You can also use break-even time. You can use all kind of indicators, but for our discussions here, we're going to be just looking at NPV. Okay, so that's what we call the value chain model, okay, that we have to create. Initially we might have very few information. We don't know how many wells, if we have network or not, what kind of offshore structure, so we have to use a simplified approach to compute these things. Okay, and that's what you will be doing in exercise 6 of the problem 6 of exercise set 1, okay, where you have to use kind of a simplified approach to estimate these expenses. Okay, while in problem 1 of exercise set 1, okay, so that's problem 6, Okay, you have to use a simplified approach to estimate cost. And in problem 1, actually you get all their values to make a proper NPV estimation. Okay, this problem which is about Block 2 in Tanzania. Okay, but let's see what, let's maybe very briefly, I think you can read it from my compendium, but basically let's say our summary of what do we have in CAPEX. Okay, more or less what are the main cost items. What I have put here, I'm not sure why, because it's not the most important, but it's maybe important for us if we are going to be working in a field development. Is called engineering studies. Okay, you need to have this team of people working on that particular project, and here you have salaries, the consultants, okay, or contractors. Okay, not a big part of CAPEX, but something we have to include. Then I wrote next, which is a big part, is the top side, the processing facilities. And what do we have here in processing facilities? We have basically everything we need to treat the fluids, reservoir fluids, and to be able to sell them in the market, okay? Which are separators, pumps, compressors, heat exchanger, I have the control system, I have the injection system if I have gas injection, okay. I have the export system, I have the treatment, water, oil and gas treatment. What else should we mention here? Well, what I call the processing facilities, and that actually is, you see, to be able to give a cost estimate, I need to know the size of the separator. I need to know how big. I need to know the wall thickness. What pressure is it going to be working with? What kind of material do I have to use? What kind of steel? Also the same thing with pumps. What kind of rates? What kind of delta P? What kind of material? What kind of... Okay. So all of these items, when I don't know much about the system, I'm not sure how I'm going to produce it. What it will be the rate per year. How is the GUR going to be evolving? Okay, how is the water cut? So to size or to estimate the cost for all of these is extremely difficult, even impossible. Okay, so I have to use approximation. Then later, when I use the feed, when I am in the feed phase, I can start to go more in detail to design each item separately. The other item cost that we define here is the offshore structure. Okay, what do we have in the offshore structure? Is simply the cost of either is a platform, okay, or I can use an FPSO, I can use a TLP, okay, the thing where I'm going to put my processing facilities on, okay, and also my people. Okay, also I have the living, that adds some to the cost, living quarters. I have the auxiliary equipment. I have the power generation system, is something that adds a lot of cost. Okay. And if it's even if it's not floating, if it's a platform, that depends very much on the weight, okay, that I'm going to put on my structure. If I put more weight, I have to need a bigger FPSO or a bigger platform. Maybe I need 2 of them. Okay. So that really depends on the facilities, what I'm going to put on top, and the facilities depend very much on how I'm going to produce it, and how will the GOR rate will change with time, water cut. So again, we have the same issue, which is a bit uncertain. Okay. Then we have, what else do we have in CapEx? If we have a subsea system, we have the subsea system cost. Where we add, for example, template. What else could we have? Flow line, pipeline. We have risers. We have umbilicals. We have also the control system. We have some metering sometimes, subsea metering. We might have some subsea processing like boosting. And lastly, I put here the export system. Okay, I think I included more or less everything here. I hope. Okay, let's go very quickly through the others. Drillex. Okay, Drillex, we have the drilling rate of the vessel that we are using. Okay, sometimes they charge some amount per day, how much it will cost. Then I have the drilling materials. Okay, here I have many things, but basically are the tubulars, casing, tubing. I have the cement. I have the mud. Also I have, if I have any well completion, usually this is also included here. The liners, I have packers, I have if I have any inflow control device, if SSV, okay, the wellhead. Here. What else do I have in drilling? Okay. I do also sometimes some tests during drilling. Okay. And that's also sometimes included as part of the drilling. Okay. I do logging, DST, pressure test, I do sampling. I put also sometimes included the Christmas tree as part of the Drillex, and then also all kind of drilling tools that I need for my drilling. Okay, but really dominating parameters here is the drilling rate of the vessel. Can be very expensive if I rent a drilling ship or a jackup to make drilling. This will be a very hefty price. Okay, it will be $500,000, $1 million, and you have to pay, and that's for example 200 to 300 days. Okay, so there, that only that part is a big part of the expense. Okay, but also the rest adds up. Few million there, few million there. Okay, like if we count every krona that we have, for them is counting every million here, million there. Okay. OPEX. What do we include in OPEX? One thing about OPEX is that it's a bit challenging to compute, okay? But OPEX actually is the operational expenditures when the field is already in operation. So that means that expense I make it much further into the future. When I buy the platform, I do the drilling, it's usually very close from when I'm planning the field. Okay? So this OPEX, as it is done much later in life, when it's discounted, it doesn't make that much impact in the NPV. Okay? On the contrary of, for example, DrillX and CapEx. But the OPEX is very important to define the abandonment rate. Okay? You always have to have enough production such that you pay for your operational expenditures. So basically the OPEX tells you for how long I will be able to produce. Okay? So I'm saying for the NPV might not be that important, but it's important to estimate. Let's put that comment here. Important to estimate abandonment rate. And of course it's changing a bit. Every time I try to make my operations more efficient, I try to reduce costs, maybe have less people, try to reduce energy consumption. That stretches a bit the end time of the field, the end time of production. Okay, but OPEX usually we include, again, not the main cost item, but really what is important for people: workers' salaries. We have insurance. Okay. We have maintenance. We have equipment that we have to buy. We have well intervention. Okay, depending on what have we decided during the phase. If the wells are very complex, they need frequent intervention. For example, they have a pump I have to change every 2 years, so I will have some intervention cost. Power consumption. Okay, and a big part of the cost is actually production chemicals. Okay, and we are going to talk a bit about that later, but actually all chemicals that are hydrate inhibitor, wax inhibitor, scale inhibitor, if I have a biocide, I have corrosion inhibitor, demulsifier, I have many chemicals that I use for on the field. For example, that will be MEG, okay, wax, you think that an associate professor at NTNU has to deal with such problems? No? That you try to write and it doesn't listen or tries to do whatever it wants with, well, maybe not a professor, but associate professor, but still, you know, I still should have some privileges. Okay, corrosion. Etc. Let's say etc. Okay, what else can we have? We can have pigging, transportation, and export. Yeah, and also sometimes we have troubleshooting. Okay, and I just want to make here the comment that troubleshooting, let's say something got damaged, you have an issue that the mixture doesn't separate as quick as you wanted. Okay, so then you have to have a bottleneck problem. Typically, the problems that I have, they don't cost too much OPEX, but they actually cost loss in revenue. Okay, which that is really the critical part. Okay, not because they are costing more, you need to buy more equipment, but actually because they are prohibiting you to achieving your levels of production that you wanted. Okay, or the highest levels of production. Okay, and then ABEX, to stop with the writing. ABEX. One big part of this cost is well plugging. Actually, here there are some aid from the government. They finance part of this plugging. A big part of it actually removal of flow lines, pipelines, removing of the offshore structure, okay, cleaning. We have monitoring. Okay, there is actually a nice article in our reference. See it here. Reference material. Okay, decommissioning, that's an article that I recommend you when you have some time to read it, just to see what kind of engineering task you have to make in okay, it's the first article that appears on this reference material. Okay, so how do we perform our NPV calculations? Okay, as you know, NPV, probably know, right, is the sum from time equal 1 to time equal n, which will be abandonment, okay, of the cash flow of year I, of that particular year. That calculation, usually do it in on a year basis, or sometimes can be more frequent, okay, maybe half a year, 3 months, but usually at early stage of field development I do it at least on a year basis. Okay, so as the cash flow, and cash flow stands for, of year I, are the sum of revenue minus the expenditures of year I. Okay, and these have to be done in dollars of that particular year, or in NOK of that particular year. Okay, and then to be able to sum all of these dollars between them, I have to discount each one of them, okay, to the power of, let's call not this I, but use another letter. Okay, let's call it maybe D, where this D is the discounting factor, discount factor. Okay, and discount factor can be a value between, is for each company might be different, but simply between 5 and 12%. It typically is within that range. Okay, and that's simply what allows me the discounting. We say the cash flow that I make in year 4 doesn't have the same value that what I made in year 1, so I have to discount it. Okay, I have to take into account this is like an inflation effect, okay, to be able to sum them. Okay, but it's not exactly inflation, is a factor that they have compared to other projects they have managed. Okay, if they say instead of having this amount of capital, instead of investing it in this project, I invest it in something else, I will get this rate. Okay, so that's the rate that I should use. It's like equivalent rate. Okay, and that's what we said initially. So expenses are executed during early years. So this factor 1 over 1 plus d to the power of I is small, so it's close to 1, sorry. Okay, I think we had a table. I think the first day of the lecture I made a table showing this factor with different years. Okay, we can try to make it once more, just to justify I didn't just talk and write, but also we had some calculation. Otherwise we become a bit politician, right? Or majoring in literature, something like that. So this discount factor, and remember this has to be expressed on a yearly basis. Okay, we are making our calculations on a year basis. This will be 0.7. Okay, and here we have the year. Usually we start year. By accounting, we have to make like what we have done in the Snow White. Okay, by the end of the year, the first year passed, and I made some expenses and I made some earnings during that year. Okay, end of year 1, and then I have this factor which is 1 over 1 plus d to the power of I. Okay, so it's 1 over 1 plus this factor, I freeze it, to the power of this guy. Okay, so you see every expenditure I make during the first phase or during the first year actually is very close to 1. Okay, but then let's say the earnings that I'm going to get, let's say I start production in year 6, year 5, year 7, they already is a factor by half of that number. Okay. So that's the expenses. That's why OPEX, let's say OPEX happens when I have already the start of production, very late. So the OPEX even might be a big number, still is discounted by those. So CAPEX, DRILLEX, they are usually much more important than everything else. But despite of that, we still make money. So it's amazing. Okay, and we can take very quickly the Snow White exercise and see how are we making our calculations. Some place here was Snow White. Okay, and that's something you have to make for block 2. We have one NPV calculations. Okay, so we have end of year. We start with end of year 1. We put all the cost. What I call usually CAPEX is capital expenditures, and it includes DRILLEX, subsea, LNG, plant, vessel. Okay, in our case, this field needs Snøhvit needs LNG vessels to take it to the customers, and it's something that is owned by the plant. Okay. Then you have the revenue. First, how much gas do I made in that year? Then I have the revenue of the sales of that gas. Okay, and then I have the cash flow, which simply is the revenue minus the expenditures. Okay. Then the discounted gas cash flow, and then like the cumulative NPV. Okay, just taking into account year 1, year 2, year 3, and so forth. So I will try to make it very quickly. How many wells do we have here? We had 9 wells. And I think here we had a constraint that each well, I think you can drill only 4 wells per year, I think. Okay? So let's say I have 9, so I have 4 year 1. I have 4, the same thing, year 2. And I have just 1. Here I have to be careful. And I have just 1 year 3. Subsea cost, pipeline and umbilicals, okay, all paid in year 1. So it's this guy here. Other thing I have to take into account is the manifold. Manifold, I have 3 templates, and each template I think is $20 million. Okay, so I have to sum that up here. I'm assuming I'm paying it in year times 3. Okay. LNG plant. LNG plant is a function of the maximum rate I have. Okay, simply a linear function. So, and I don't know exactly. Let's say we also paid in year 1. So we say LNG plant is this number times the maximum rate, and the maximum rate we were producing was, I think, 20 million, right? LNG vessels. How many vessels do I need? Each vessel costs 20 million, 200 million. Okay, and every one can transport 86 million standard cubic meter of gas. And they can do 20 trips on a year. I leave that to you, okay, to calculate how many, because we are now close to the end. Okay, total capex, we say drill legs, subsea, LNG plant, the vessels that I have, and I simply drag it down. Okay, all of the rest will be 0. I have no more drill legs usually, unless I want to make infill drilling to maintain production. Subsea, I don't have any more expenditures in subsea, only during operational expenses. And the LNG, we know is not 0, but we're going to use 0. Gas offtake, how much I took that year. Yep.
But for the LNG plant, since we're saying it's at maximum flow rate, however, shouldn't that be based on the number of wells that we have? So we're not going to have the maximum from the first year, it's going to be up to the third.
No, simply that's how much it costs to get the plant for 20 million,
So
to
the
process
plant that
20 million.
produces this much.
Yeah.
Okay.
Okay, it's a plant that has to be able to take 20 million.
So it's not the operation of the
No, it's the how much the acquisition, design, commissioning of the plant. Okay. In a very simplified way, that's like a lump sum taking everything. Okay. In reality, to get that number, you will need maybe a month or 2 months to get the number from a company. Okay. Yearly gas offtake. Then we come here. We had a column very convenient called delta GP. We don't have. Okay, we just have GP. How do we calculate delta GP from GP? The production of gas during that year. We're just going to finish, just have some. Okay, during the first year I produced this much, right? And I simply drag it down. Okay, So you see I'm producing in plateau initially, and then finally I enter into decline. Okay, and I should have done it until abandonment rate. When do I start production? I'm not sure. I should have. Yeah, let's say we start production in year 6. Okay, here. So I'm having 5 years to build the field, and then I start production in end of year 5, just beginning of year 6. Okay. Revenue, initially I don't have any revenue, but I have, then at year 6 I start to sell this gas, and the price of the gas is here, gas price. Okay, I block it. I don't have any condensate, I don't sell anything else from this plant, so I just sell the gas as LNG. Cash flow then becomes the revenue minus the expenditure. Okay. Then the discounted cash flow is that number divided by 1 plus this interest rate, discount rate, okay, that I have to divide by to the power of the year. Okay, and something that I didn't block. This guy. Okay, finally NPV will be, here will be this guy, okay. And the next one will be this guy plus the previous, right, for each year. And I shouldn't have these numbers. Scientific, okay. So you see it doesn't change after, because we don't have any more production and we don't have any more expenses, so I should have done my calculations down to year 30. So it's 7.5 billion, I think that's in dollars, yeah, 7.5 billion dollars, the value of that project. Okay, more or less clear. Was a bit quick, but you know, we don't have much time. So let me see you on, first, do you have any questions before we close our session? Yes?
How would you categorize the tax burden?
The?
Would you consider the tax burden to be an OpEx?
The tax? No. I can send you some material on that, how to include tax. Okay? But for that, as I told you, you go better to the class of Trygveström. Okay? But essentially, we have different type of taxes. One is of the brutto sales that I get. Okay? And then I have some of the net income, okay, a percentage of the net income, and actually those percentage they can change a bit during the first years of production. Okay, I get some, I think, some tax incentives where I pay less initially and then I start to pay more and more. Okay, but it's not so simple as to include as an OpEx. Okay, but OpEx affects my net income. Okay, affects the net income over which the tax is calculated. Okay, any other question? No? See you on Friday. Have a nice week.